So the final talk of the day will be Andrew Fulcher to tell us about the cyclic flats of L-polymatroids. Please.
Is this, yeah. Thanks, Alex, and thanks for inviting me here. It's been fun and educational, and I'm sure the rest will be as well. So my talk is going to be largely singing the praises of cyclic flats, of matroids, Q-matroids, polymatroids, and then a generalization of those L-polymatroids. So it'll be quite light, but hopefully my goal is that if you're not already interested in cyclic flats, you'll look into them a little bit. This is based on a paper that was joint work that I did with my supervisor, Emer Byrne, at UCD, University College Dublin. So quick introduction on cyclic flats. So let M be a matroid defined as set and rank function and star its dual. A set is cyclic, subset of S is cyclic if it's the union of circuits, minimal dependent sets. And a subset is a flat if when you sort of add anything to it, you increase the rank strictly. And a nice thing that has some uses, certainly in Q-matroid theory, is that the complement, or let's say the dual, of a cyclic flat is a cyclic flat in the dual. So here I've written the same definition for flat as I've written here, but for cyclic, another way you can think about this is that if you take any singleton away from the set, you don't decrease the rank. It's a convenient way of thinking about it. So there's a paper from 2005 by Bonin and Demir where they characterized matroids via a set of axioms on the cyclic flats, so made a cryptomorphism. So in this paper, they proved that these objects within the subset lattice is itself a lattice, and the matroid is determined uniquely by the embedding of this lattice into the subset lattice and the rank function of the matroid restricted to that lattice that I'm using calligraphic Z for. Yeah, they made an axiom set that's cryptomorphic to the other ones. One immediately nice noticeable thing about cyclic flats is that there are far fewer of them than there are elements in the subset lattice. So in some sense, you are looking at key features of the rank structure of a matroid. Same will go for Q-matroids and polymatroids. I'll give an example later of a Q-matroid that has a pretty dramatic difference in the numbers. Okay, so I'll give here some instances of why one might be interested in cyclic flats. There are numerous more examples, but here's just a few for matroids. So let M be a matroid and calligraphic Z, its lattice of cyclic flats. So the top polynomial can be computed from not just the lattice of cyclic flats, but an isomorphism class of the lattice of cyclic flats, as well as the rank function restricted to this. So in some sense, these lattices, not even the elements within them, but just the isomorphism class of each one is enough to characterize the top polynomial. So it does sort of tell you something about the top polynomial. the free product. Don't know if any of you have heard of that. It's kind of a cool operation. You heard of the direct sum being talked about in Janira's talk a few talks ago, and Peter gave a question about that. One of the answers of why something could, in spirit, be considered a direct sum is if you have two matroids, Q matroids, whatever, and you want to sort of put them together such that you sort of embed them in a larger matroid, and you have that the restriction to some element in this subset lattice is one matroid, and the restriction is the other matroid. It's the most dependent matroid that satisfies those parameters, and the free product is the most independent one. So that's kind of an interesting one, if you've looked into that. So some progress has been made towards characterizing the lattice of cyclic flats of representable matroids. I mean, that would be very nice, right? But not sure a whole lot of progress has been made there, so I guess it's pretty hard, but maybe there's some possibilities there. So yeah, there's loads more. The objects that I typically look at are generalizations of matroids. So there are different ways of generalizing them. I mean, Peter gave one in his talk yesterday about allowing the sort of ambient structure, let's say, that you put matroid stuff on to be infinite. I'll go through two ways here. Q matroid, I'll breeze through this one because you've seen this definition a few times today, so vector space things. And a polymatroid is another one. So the main difference, the only difference between a matroid and a polymatroid is this second one. So typically you have in this setup that the rank of X is no greater than the rank of Y is no greater than the cardinality of Y. So, well, actually, I suppose there's another difference. Probably should have written, well, I should have written here that the rank function sends, is from subsets of this ambient set and sends it to the real numbers. So it can be any real number and it's not bounded above by the cardinality of a set. But apart from that, it's the same. So these L-polymatroids that I'll be talking about in a little while sort of combine these two ideas. And I'll be talking about cyclic flats for each of these two, which have previously been developed, and then cyclic flats for L-polymatroids that me and Emer Byrne developed. So for Q matroids, cyclic flats were developed in 2022 by Janira and Emer Byrne. So in that paper, you're going to see a bit of repetition here, but I did that on purpose to show I don't know, to just give a bit of like the spirit that I see in cyclic flats. That cyclic flats, they will all, in each of these cases, form lattices, and these lattices are not necessarily, they don't necessarily have any properties other than being finite. Like that's a theorem given by Bonin and Demir. So you can, with a lot of results, if you have the result in, not all results obviously, but if you have the result in matroids and you can characterize the results via cyclic flats, you can quite easily, trivially sometimes, just have that results for Q matroids. So in that paper, they have these three results, just the exact same as before, but for Q matroids, it's a lattice. By inclusion, it's determined, the matroid, well, the Q matroid is determined by this lattice embedded into the subspace lattice. That's what this LV is, and the rank function restricted to Z. And they developed a set of axioms and cryptomorphism. I wanted to include one quite nice application. Janira talked about this in her talk, so it's not the surprise I hoped it would be. But so with the direct sum of Q-matroids, it's pretty tricky. The definition is quite convoluted. It's in a paper by Urias and Cheria. But things like independent spaces, flats, circuits, spaces, they don't transfer nicely from if you have the two of them for M and N to the direct sum. But cyclic flats do, and so you can characterize the direct sum via cyclic flats, or if a Q-matroid or matroid is connected or not based upon the lattice of cyclic flats, can that be decomposed into some sort of direct sum? Okay, so a picture would be nice. So it was really convenient for me, so many of the talks that preceded mine. If you remember Peter's talk with the colors and the lattice, so this is, so X here is a cyclic flat. Any lattice element, so in Q-matroid, any subspace that is, that contains it and the codimension is 1, has a red cover, the rank goes up by 1, and any below it, it doesn't go down by 1. That's what a cyclic flat looks like. And here's an example from a paper by Glusing, Lursen, and Janey from 2023 of how much smaller, I mean, this is presumably a particularly dramatic example, but there are probably lots of examples, I suppose, when you go to larger dimensions of the information that you sort of save in a way. So let a vector space be 8-dimensional over binary field and take some canonical basis of it. Okay, we'll go through this next part. So the lattice of or this Z is going to be going to have 5 elements, Z0 to Z4. Z0 is going to be the 0 vector space. Z1 is going to have 2 dimensions. Z2 is going to contain Z1 and have 4 dimensions. Z3 is going to intersect trivially both of those two, and Z4 is going to be the entire vector space. So this is a lattice, and it does satisfy the axioms that I alluded to previously. And based upon these axioms, you can reconstruct the matroid or Q-matroid or whatever as you would expect. So here they let the rank function, this OR hat, defined on this Z here, equal I for Zi, and then defined the this OR function based upon this expression here. That's generally what it looks like, something like that when you reconstruct the Q-matroid based upon the lattice of cyclic flats. But that's not important now. It is indeed a Q-matroid, and we'll look at the statistics of it. So it has 100,000, hundreds of thousands of flat cyclic spaces independent of these things, but it has 5 cyclic flats. So that's quite a bit less than hundreds of thousands. Okay, so that's a bit on Q-matroid cyclic flats. Now I'll go through polymatroid cyclic flats. So they were defined in 2019 by Laszlo Surmaz. So this is going to be another one of those repetition slides. So take some polymatroid and its lattice of cyclic flats. Is there a, do I have to direct it? And it's the polymatroid is determined by the lattice of cyclic flats embedded in the subset lattice. This is sort of 2 to the S if you take S as the ambient set, and the restriction of the rank function to this lattice. But you also have another piece of the puzzle for polymatroids. Like, you probably could define a sort of canonical polymatroid based upon a lattice of cyclic flats, but you do have the possibility of defining different atomic weights, so the singleton sets, the sort of ranks of those. So you also need to know the rank function restricted to singleton sets. In that paper, a set of cyclic flat axioms were given that give a cryptomorphism. So for polymatroids, it's more complicated to give a picture, so I'm going to give a picture of what a cyclic flat with two elements would look like. So this xy is a cyclic flat. Anything above it, if you add anything else to that set, the rank goes up, so it is a flat. But below it, it's a bit different. So I use these colors to help. I am sorry if anyone has difficulty discerning between these colors. So this, in order for this to be a cyclic flat, either this cover, the yellow one, has to either be 0 or has to be strictly less than this black one. Now, by submodularity, it's always going to be no greater than the black one, but it has to be strictly less than it, as well as this red one being either 0 or strictly less than this blue one here. Now, onto the objects that we defined cyclic flats on. Okay. So we assume that this lattice is finite. L-polymatroids give a generalization of Q-matroids, polymatroids, and rank metric codes, if you like those. An L-polymatroid is a lattice and a function from the lattice to the reals that satisfies these unsurprising properties. It's pointed, 0 is 0. It's increasing, not bounded above, as is typical of polymatroids. It looks exactly, you'll see we have used lattice, meet, and join rather than like union and an intersection. But other than that, it's pretty much identical to the definition of a polymatroid, but the underlying structure is more general. So cyclic flats. So yeah, that previous definition was just on any finite lattice. There was no restrictions made on it. But for cyclic flats, we did have to make the restriction that the lattice be modular and complemented, which is fair enough, I would say. If you looked at these things before, there's a lot of lattices, including vector subspace lattices, that these comprise. So modular, Peter went through it in his talk. It's lattice is satisfying this equality whenever x is less than y. Quite an easy way to think about it is that all chains between two elements are the same length, but that's not the entire picture, because you'll have non-modular lattices that satisfy that. But it's a very useful property, and you'll see it in a lot of places, but before you've kind of played with it a bit, it does seem a bit unintuitive. Complemented, you'll have seen this before. You take the complement of something and the union is the whole thing, and the intersection is nothing. But in more general lattices that are just complemented, you may not have a unique complement. And some terminology, one element covers another if it's above that element and there's no element strictly between them. So in the paper that this talk is based on, we generalize the definition of a cyclic flat. This will be the flat part. All right, nothing changes there. Now this is the cyclic part where it changed quite a bit. So if y is covered by x, so if x, y is below it, there exists some atom, so a complement of y, because x is going to equal y join a, and the difference in rank between x and y is strictly less than a if the rank of x is not equal to the rank of y. So this is very similar to the definition we saw by Surma's, except you just, the decision when we were making this definition is it there exists or is it for all, right? Because in the subset case, there's only going to be one unique atom that satisfies that. So there exists was the better choice because that generates a lattice. Okay. And then, yeah, another repetition of this style of slide. Then to summarize the theorems in our paper, this set of objects is a lattice by inclusion, determines the L-polymatroid with, restricted to the atoms as opposed to singletons, and we have cryptomorphisms with the other L-polymatroid sets of axioms. So here's a quick example to finish on. So here are, it's going to be color-coded, so the following lattice that you'll see in a moment is the subspace lattice of 3 dimensions over binary field. Cyan is 3, black is 2, red is 1, green is 0. So here's an example of an L-polymatroid, a Q-polymatroid if you like, because it is a subspace lattice. And there are two cyclic flats in this. Rutger, can you tell me what they are? Sorry, I'm only joking. I was trying to be mean. Here's one, this one here, because anything below it, this is 0, right, is, the y below the x is equal in rank. It has to be 0. It can't be in anything else because you don't have a complement of it. And then the only other one is this one up the top, right? We don't have to worry about these green ones because they satisfy the equal one. So what about this red one? Well, this red is a 1. So what's a complement of that? Well, this blue one is a 3, and that's a complement of that, so we're good there. This black one is a 2, and the blue one is 3, is a complement of that. So you get, that's the lattice of cyclic flats. That's the end of the talk. Thanks for listening.
We have time for a question or two.
So you're saying that I'm talking about lattices here. So what's my approach to matroids? I don't think about where it lives. I think about these lattices and these colors typically. Well, I mean more sort of values rather than specific colors. That's how I think about them.
All right, let's thank Andrew again.